Look up. When you peer at the heavens on a clear, moonless night, you can see the stars of our galaxy strewn across the black. We cannot help but seek recognizable outlines by tracing our finger from one star to the next, like searching for shapes in clouds. We see ourselves in the groups of stars, assigning them names and meaning. To our eyes, the individual stars making up these constellations seem uniform, remarkable only when forming part of a larger group. But with a powerful enough telescope, the truth reveals itself, and we can finally reshape the sky according to science, not symbolism. So let us take a tour of the stars, in order of their rarity. We begin with the failed stars, brown dwarfs. Below 8% of the mass of the Sun, these are protostars without the gravitational clout to spark fusion in their cores. The galaxy is littered with these failures, one for every successful star. Stars in the prime of their stellar lives make up 90% of the several hundred billion in the Milky Way. Our Sun is one, part of the yellow dwarf category in which only about 7% of stars fall, a relative rarity. Far more numerous are the cooler and smaller red dwarfs that make up a much larger 75%. As we look for stars with larger masses, the search becomes more difficult thanks to their volatility and short lifespan. White supergiants like Canopus, the second brightest star in the sky despite its great distance from us, comprise less than 1% of the stars in our galaxy, and more extreme hypergiants, like the largest known star Stevenson 218, are even harder to find. Their size resulting in strong stellar winds, where stellar material the mass of Jupiter is blown away in single events, almost evaporating the star as fast as it grows. While most stars are enjoying their best life, there are tens of billions in the final stages of their stellar evolution. Smaller stars, such as the Sun, will eventually puff out into red giants, a fleeting midpoint on the way to a white dwarf. These dense and compact stellar remnants comprise about 5% of stars in the present day, though eventually 97% of the Milky Way's stellar population will shrivel into these gently fading spheres. Neutron stars and black holes are exotic high-density phenomena, making up 0.5% and 0.0005% of our galaxy's population respectively, and the result of supernovae by their largest stars. While spinning neutron stars, pulsars, have been observed in their thousands since the 1960s, we have only observed 31 of their most extreme form, magnetars. This type of neutron star has a magnetic field 1,000 trillion times stronger than that of the Earth, and starquakes on their surface produce powerful bursts of gamma rays. These starquakes are also much stronger than our equivalent, reaching up to 23 on the Richter scale. But even that is still not the rarest form of star scientists predict could be out there. In its early days, the universe was filled with hypergiants, but they were much different to those we see now. The first lights that kindled in the cosmos were vast, hungry, and short-lived, living and dying in a cosmic blink of an eye. Known as Population 3 stars, they were the ancestors of us all, and they may still linger out there in the black, the rarest stars in the universe. How much time do you have? A Planck time is the shortest possible moment of time. An average human life is about 4 to the power of 52 of these single moments long, more than the amount of atoms inside the entire Earth. And on average, your career makes up 80,000 hours of that total, roughly 20%, and so is a huge opportunity to make a positive difference in the world. 80,000 Hours has sponsored this video, and they are a non-profit that helps people find a fulfilling career that also does good, and everything they provide is free, forever. Based on 10 years of research with academics from Oxford University, their aim is to help you find a job that makes a positive difference in the world, helps solve the biggest problems facing humanity, and also gives you job satisfaction. A lot of career advice focuses on a few well-known paths that people think have a high social impact, like being a doctor, teacher, or charity worker. But it turns out these aren't your only options to be a force for good, and they probably aren't your best options either. Everything 80,000 Hours publishes is based on careful consideration of the best evidence they can find on the topic. Their in-depth, research-led career guide has also just been updated for 2023, and if you join the newsletter now, you'll get a free copy sent directly to your inbox. So, to get started on planning a career that works on one of the world's most pressing problems, sign up now at 80,000hours.org/universe. Thanks to 80,000 Hours for supporting education on YouTube. In Japanese mythology, the god of creation gives birth to many deities, but 3 are particularly divine. Tsukuyomi, the moon god, Susanoo, the god of storms and seas, and Amaterasu, the goddess of the sun, the highest deity of all. In the most famous legend involving the sun goddess, Susanoo threw a holy horse into a loom, flaying it alive and killing a nearby weaving maiden. Amaterasu was so upset that she fled and hid in a cave, blocking the entrance. The sun disappeared from the sky, and a permanent night fell on Japan. This eternal night only ended when the other gods and goddesses staged a ritual outside the cave, laughing so loudly that Amaterasu could not help but come out to see what was going on. The deities sealed the cave shut as she emerged, and Japan, once again, became the land of the rising sun. The sun is essential to all life on Earth. Its calm and predictability nurtures plants, animals, and humans alike, surrounding them with light and warmth. It is no wonder then that right from when the earliest civilizations formed, the sun has often been portrayed as a benevolent god, one to be feared perhaps, but only because of its possible disappearance. Now, of course, we understand that stars are physical entities, still full of wonder but explainable using modern science. For the longest time, we were reliant on only our own eyes, until Galileo ground his artificial lenses and magnified the skies with his telescope. The haze of the Milky Way resolved into millions of stars, and even some individual stars revealed themselves to be binary systems. Hundreds of years passed, and we catalogued the positions of these stars with increasing accuracy. And with the advent of spectroscopy, we could even begin to identify barcodes individual to each star, the gaps in which revealed which heavy elements were present in that stellar atmosphere. We could identify what these distant suns were really made of. But that was not all. All chemical elements comprise a nucleus surrounded by electrons. These electrons naturally rest in the ground state, but can be excited up into different energy levels by the absorption of a photon with an energy equal to a particular energy gap. As photons of all energies struggle from the core of a star through its outer layers, chemical elements within the star will absorb photons with energies equal to each element's specific electron energy gaps. The energy of a photon is proportional to its wavelength, and so photons of certain energies, certain wavelengths, absorbed by certain elements in their escape from the sun, will be missing when they reach our telescopes. Our sun emits light across the electromagnetic spectrum, peaking in the green wavelengths, but its spectrum is full of gaps, absorption lines, that tell us what elements are present and also the temperature of the stellar atmosphere. Absorption lines attributed to a specific element have been measured in laboratories and are the same wherever we observe them in the universe, except for one key feature. They vary according to temperature. Higher temperatures result in the excitation and release of electrons, changing the energy gaps, and so the pattern. And this means that we can use the color of a star to figure out how hot it is. In the 1860s, Italian astronomer Angelo Secchi was one of the first to divide stars into categories based on spectroscopy, noticing that stars of similar color have similar spectra. Cooler stars are red, the lower energy end of the spectrum, and blue stars are hotter. And so finally, there was a way of grouping the stars other than imagined patterns because of their apparent closeness. But at the turn of the 20th century, teams of women at the Harvard Observatory went one step further. Known as the Harvard Computers, they were methodically studying thousands of glass plates per day. Small sections of the night sky were imprinted on the glass, a tiny spectra accompanying each star. Women such as Annie Jump Cannon and Wilhelmina P. Fleming had initially been hired as cheap labor, but their knowledge of the skies was unsurpassed. Soon, a system was created whereby stars were sorted into alphabetical categories according to the features in their spectra. Over time, with more understanding of the physical processes determining absorption lines, these categories were reorganized and merged into the categories that persist today: OB, AF, GK, MN. Often remembered using the mnemonic, "Oh be a fine guy, kiss me now." Astronomers had created a system to organize the stars above, but they still believed they were all fundamentally the same, differing only in temperature, even including planets in this approximation. After all, the spectra of the Sun showed the presence of elements found on Earth: carbon, oxygen, and iron. Bread is bread, whether heated or toasted. It is the similarity of ingredients that defines it. Until 1925, the Earth was seen as simply the cold end of a temperature classification of stars. The Sun was just a hot Earth. This was because astronomers had mainly been focusing on the presence or absence of a chemical's barcode, not how much of that element might actually be present. This required a far more complicated calculation, where the relative ionization states of each element would need to be taken into account. And it wasn't until 1925, when British-born astronomer Cecilia Payne finally did that calculation, that the true interior of our local star was revealed. She determined the mass of the Sun to be 98% hydrogen, the heavy elements just a garnish. The ingredients of stars and planets were largely the same, but the relative amounts of these ingredients were completely different. There was no way that these two entities could be of the same category. This result, however, ran so counter to established knowledge that Payne's thesis was not accepted in the scientific world, and she eventually moved on from the subject. Indeed, even she wasn't entirely sure of her idea until it was independently confirmed 4 years later. Her limelight lost, her moment gone. To quote Payne, "Do not undertake a scientific career in quest of fame or money. There are easier and better ways to reach them." And so once again, the perspective shifted. Stars were not gods, but they were not hot planets either. They were something unique, superheated balls of gas releasing enormous amounts of energy. There now existed two categories: planets and stars, with the latter subdivided by temperature. But the garnish of heavy elements present in the Sun was not to be discounted, for it would be the key to breaking the remaining assumption that all stars were the same. In the 1940s, Walter Baade noticed differences in the stellar spectra from stars in different locations in the galaxy. The dust had only just settled after the split of stars and planets, and now Baade was proposing a further split within the stars. In our galaxy's spiral, where stellar nurseries were prevalent, the spectra of the young stars had stronger absorption lines, indicating a larger abundance of heavier elements. These he named Population 1, a category that includes our Sun. In the ethereal halo of the Milky Way, however, the spectra suggested the stars contained fewer, heavier elements. This halo is the retirement home of the Milky Way. They were named Population 2. But that was not the end, for even those stars still contained some heavy elements. They were not totally unpolluted. And so the question lingered: were there even purer stars hiding out there in the depths of space? Was there an even older population waiting to be found? In 2022, a team of astronomers from Johns Hopkins University was scouring images from the Hubble Space Telescope for hints of the earliest galaxies, when they found something totally unexpected. Hubble has produced beautiful images of nearby galaxies in intricate detail, pinwheels, galaxies bright with star formation, and even galaxies colliding. But as we look farther away, and thus further back in time, the images become increasingly murky, smudges of ill-defined colour. However, as the scientists peered at one of these distant galaxies, they noticed a pinprick of detail, a single star, clearly picked out from the amorphous background galaxy, almost as if it had been lined up with a magnifying glass. It was named Earendel, or Morning Star in Old English, and was calculated to have been born less than 1 billion years after the Big Bang. Believed to have been between 50 and 100 solar masses with a surface temperature of 20,000 Kelvin, over 3 times hotter than our Sun, we would not normally be able to see a star so far away. But here we were lucky, for there had been a chance alignment with a cosmic magnifying glass, a gravitational lens. Massive clusters of galaxies produce such a large gravitational pull that the light from background stars is bent around the cluster, just like light bends along with the lens shape in a magnifying glass. Stars and galaxies that would otherwise be hidden behind the cluster of foreground galaxies have their light projected and magnified around the cluster. Astronomers use this effect, gravitational lensing, to see objects too faint or too far away to see otherwise. But of course, we cannot choose what to magnify. That is up to luck, and the chances of a single star so precisely aligning with the focus of the lens were astonishingly small. For Earendel, the galaxy cluster had magnified and distorted its host galaxy into an arc, typical of a strong lensing effect. Its image had been enhanced 1,000 times over, making it seem bigger and brighter than all the stars in the galaxy surrounding it. This wasn't a new phenomenon, indeed Einstein had predicted it at the beginning of the 20th century. But there was something else about Earendel that left the astronomers in shock. The colour of its light. Light has unique properties depending on its energy. The electromagnetic spectrum stretches from low energy, long wavelength radio waves, through the infrared, a rainbow of optical light, and up to the high energy, shorter wavelength UV, X-rays, and gamma rays. When a source of light is moving away from us, we observe the starlight is shifted down the spectrum to longer wavelengths because of the expansion of the universe. The light we are observing is of lower energy, redshift. The expansion of space-time is such that we observe further galaxies as travelling at faster speeds away from us. Thus, we will see larger redshifts from the farthest galaxies that are moving the fastest away. And Earendel's light was very red indeed, placing it at a vast distance. The light from this star had taken 13 billion years to get to us, placing it close to the era of the first stars. Yet despite its light living on, stretched across the galaxy-spanning lens, distant Earendel itself is no more. The eventual fate of a star depends only on its mass. A star dies when gravity wins the fight against the pressure created by the atoms in the core of the star. Here, the immense gravitational pressure causes hydrogen to fuse into helium, releasing energy and heat, balancing the inwards force. Once the hydrogen in the core has been all used up, the core contracts and the fusion of helium begins, while the fusion of hydrogen proceeds outwards in a shell surrounding the core. For stars below 8 solar masses, the outer layers of the star inflate in a balancing act with the contracting core, and the star grows to become a red giant. When the Sun evolves into a red giant in 5 billion years, it will envelop the orbits of Mercury, Venus, and possibly Earth. In these smaller stars, which nevertheless comprise 97% of the stellar population of the Milky Way, the temperature in the core is not sufficient to fuse carbon, and so a core of inert carbon builds up. The fusion reactions stop, and the outward pressure provided by the energetic products of these reactions suddenly drops. Like a tug of war where one opponent lets go, the opposing gravitational force pulls the outer layers, collapsing the star into a white dwarf, a stellar remnant held up by the pressure of the electrons in the atoms. But for stars with a higher mass, a more violent end awaits. Above 10 solar masses, the temperature is high enough that fusion can proceed through increasingly heavier elements. A cross-section of the star would show a core of inert iron surrounded by shells created by the outwards progression of fusion of lighter elements. When it comes to the formation of iron, though, fusion is no longer so energy efficient. The fusion of iron consumes more energy than it gives, resulting in another sudden loss of pressure. This time, the mass of the collapsing shells is so great as to overcome the electron pressure that holds up the layers in a white dwarf. The star continues collapsing to an even denser remnant, a neutron star. This ultra-dense mass of neutrons finally provides the force necessary to stop the gravitational collapse. The event is so sudden, though, that there is no gentle release of the outer layers into a planetary nebula. This time, there is a bright explosion, a supernova where all but the neutron star remnant explodes into the surroundings. The truly massive stars, tens of solar masses, will leave remnants that, following the supernova, are still too massive to compete against their own gravitational collapse. Gravity wins completely. The neutron star collapses in on itself and forms a black hole, a point in space-time so dense that even light cannot escape its gravitational pull. All these outcomes depend on mass and result in counterintuitively shorter lifetimes the more massive the star. The more massive the star, the more hydrogen fuel there is, and so one would think the longer this process can continue. However, the more hydrogen, the more gravitational pressure the star is under, and the faster the fusion process needs to progress to create a higher pressure. The more massive the star, the shorter the lifetime, and the more violence it is met with at the end. Arendel's mass is such that we know it will have perished in a supernova within millions of years of its birth. And these supernovae are key to our understanding of the different populations of stars, Population 1 and Population 2. The explosion spreads the newly created heavier elements into the surrounding gas, which, when it cools, will go on to form the next generation of star. Walter Baade had found two distinct populations with different heavy element content, but this was not a transition over a stellar lifetime. It was an evolution of the properties of stars over the universe's lifetime. Generations of stellar formation, death, and rebirth were creating stars with increasing levels of heavy elements. Two populations of stellar evolution are as divergent and yet related as the mammoth and the elephant. Over generations of stars, more heavy elements are created and spread into the interstellar medium through powerful supernovae. Successive generations of stars form from richer gas, and so begin their lives already composed of a lower fraction of hydrogen. Astronomers could follow this timeline easily enough, but it left them with a question. What if we continue looking back into the darkness, rewinding time from Population 1 to Population 2 and further, such that the stars were made from purer and purer gas? There must have been a common ancestor born to a universe so new and untouched that it was made of just hydrogen and helium, but for a scattering of lithium and beryllium, the only other two elements around after the Big Bang. Were these the first primitive stars? Where was Population 3? The light from Arendel is ancient, but there are enough hints of heavy elements that it is unlikely to be of the oldest generation of stars, though only further observations of its spectrum by the James Webb Space Telescope will tell us for sure. And the observation of Arendel was already record-breaking. It didn't just improve on the previous record for farthest star observed, It smashed it to smithereens. And it might be a record that is here to stay. The light from Arendelle is so faint that had it not been so perfectly aligned with the cosmic lens, we would not have seen it at all. And there is no guarantee that we will chance upon another galaxy cluster with a similarly serendipitous alignment. Even if we were so lucky, stars any farther away than Arendelle and so from an earlier time might be too faint to see even with lensing. Much closer to home, back amongst our constellations, we can dive into the Orion Nebula and see how modern-day stars come to life. It is a dynamic environment, full of the gas and dust needed to form nascent suns. But despite this nebula being a typical stellar nursery, the surroundings are nothing like those that created the first stars. They would have been born into a very different universe. Population 3 came into being in a more primitive, calmer environment. Pure darkness. About 100 million years after the Big Bang, there was just hydrogen and helium, a smidgen of lithium, but no trace of the heavier elements. This simple gas gathered together under its own gravity following the scaffolding of dark matter hidden throughout the universe. Forming a star is a precision process. If a gas cloud is too small, fusion cannot ignite, and the gas cloud is doomed to become a brown dwarf, a failed star. If a gas cloud is too hot, then the collapsing cloud will meet resistance from the gas pressure and end up dispersing. Any gas will naturally heat as the cloud collapses and pressure increases, just as your bike tire becomes warm when inflating. Somehow, this energy must be carried away to prevent the cloud dispersing, but not in such an explosive way as to reverse the collapse. In the Orion Nebula, the gas is rich with heavy elements. Collisions between the atoms within the gas cause electrons to climb up the energy levels, releasing photons as they naturally descend again. These photons are free to flee the system, packets of energy that were once embodied in the kinetic energy and pressure of the gas. The heavy elements have many energy transitions, and losing energy in this way is easy. In the primordial universe, however, the stars must make do with the energy levels available in hydrogen and helium. The energy loss is far less efficient, and so clouds more easily disperse as they collapse. Only the truly massive clouds can produce the gravitational pressure that can sustain collapse throughout that inefficient heat loss. Gently, gently, these lucky clouds collapse until the pressure in the core is so high as to start the process of fusion. The first stars begin their lives as giants, battling the constant pressure of gravity, fusing hydrogen and releasing the photons that light up the universe for the first time. But, just like Arendelle, these massive first stars are long gone. Our Sun will have a lifetime of approximately 9 to 10 billion years, of which it is halfway through. In comparison, the first stars of 100 times the mass of our Sun will live a few million years at most. It is the 3-day life of a fruit fly compared to that of a human's. Of course, the light of Population 3 is still travelling across the expanding universe, but it is too faint for us to make out without the chance magnification of a gravitational lens. And so, are we doomed to place our hopes on another such serendipitous alignment? Is this old light all that is left? Is all we can do wait? Stellar archaeologists aren't so sure, and they go further. They believe we can not only observe the old light of long-dead first stars, but the first stars themselves. Over 500,000 years ago, on the island of Crete, there once lived a population of mammoths. Mammoths are extinct, victims of a change in the climate and hunting by early humans, but we have learned about their importance in prehistoric human life through cave art. Rufinyak Cave, a UNESCO World Heritage Site, is known as the Cave of 100 Mammoths. Mammoths account for 70% of the animals depicted, and looking at the simple lines of their tusks and bodies, it's easy to see why these extinct creatures still hold our fascination. They were daunting beasts, reaching about 4 meters in height, a species where gigantism was normal. But not on Crete. On several islands around the world, island life encouraged these mammals to evolve smaller and smaller bodies. We use the word mammoth colloquially to mean anything gigantic or outsized, yet the pygmy mammoth of Crete reached only 1 meter high. Insular dwarfism is a well-known evolutionary effect, whereby species evolve smaller versions of their bodies to fit in with a smaller environment, most often on an island. Pygmy mammoths existed in pockets around the world. While mammoth skeletons are common in museums, the bodies of these miniature mammoths are far rarer because of their lower numbers. And so too, the first stars were mammoths by nature. But, just like the evolution of life on Earth, the quickly changing universe led to pockets of smaller, pygmy, population 3 stars. And a smaller mass means a longer lifetime, so if we search the islands where they still live, we might just find one. As the first stars die, they explode and seed the pristine universe with heavier elements. No longer just hydrogen, helium and lithium, but beryllium, carbon and oxygen, the ingredients for planets and life. So efficient is this seeding that the first generation of population 3 stars is also the last. Only a few million years after the darkness ended, no corner of the universe remains pristine. Population 3, the primordial stars, can no longer form. But why should we care about these first stars? Why not just study those close to us that still live and are easily observed? First, they help complete our knowledge of modern-day stellar astronomy. Population 3 stars are chemically so different to their modern-day counterparts that the fusion reactions and energy transfer processes that power them are quite unlike what we see in stars like our Sun. Secondly, the first stars were responsible for the greatest chemical evolution event our universe has ever seen, a sudden spark that began billions of years of heavy element manufacture. And last of all, simple curiosity. These stars are extinct. The window of their existence was a cosmological blink of the eye, a few million years over 13 billion years ago. They are a dinosaur, a dodo, a mammoth, imbued with a mystery astronomers can't resist. Their short lifetimes, however, would appear to leave little hope for observation. Except for the fact, like mammoths, stars form over a range of sizes. Massive stars do indeed dominate in this time as a rule, but every rule has an exception. Just as our time sees small stars dominate with few massive stars, the era of the first stars may have contained many massive stars, with a sprinkling of smaller. And astronomers have only been equipped to consider the possibility of these smaller stars in the last few years, through more and more powerful computer simulations. To accurately simulate a star formation region, you need an N-body dark matter simulation, coupled with a way to calculate the physics of the gas. N-body simulations are so called because they apply physical equations to a certain number, n, of discrete mass particles in the simulation space. Imagine a room of 25 people. These people are interacting all the time, moving between conversations, clustering around particularly entertaining individuals, breaking off into groups. In a low-mass resolution N-body simulation, we might have only 5 particles, so we would have to represent 5 humans per particle. We wouldn't be able to capture the smaller movements of the individual, only the larger movements of the groups. Whereas in a high-mass resolution simulation, we could perhaps apply a particle for each human, picking up all the interactions. But this will be a far more complex calculation. And so, if we are restricted to 5 particles but interested in how an individual conversation plays out, we might perhaps choose to zoom in instead, assigning one particle per human, but focusing only on one group of 5. And so in simulations of star formation regions, the movement of the dark matter particles under complex gravitational interactions is calculated over time steps to find the scaffolding upon which the hydrogen comes together. You then have the choice to either run accurate hydrodynamical simulations, which calculate the movement and physics of the gas in a similar manner, assigning a certain number of particles, or make sweeping assumptions and model the gas physics analytically, with a few short equations applied generally to the whole box. For a long time, it was assumed analytically that all the gas in the area surrounding a protostar would, over the course of thousands of years, accrete onto the star, leaving nothing else. It was assumed the first stars would be lonely. However, more recently, computing power is such that we can use some of the biggest supercomputers in the world to run simulations with a finer mass resolution over the region surrounding the protostar. These simulations have revealed a disk of matter that flattens like a pancake when the cloud collapses and rotates, like a chef spinning pizza dough. This accretion disk of gas and dust is a crowded, turbulent environment, causing the disk to fragment. Astronomers then applied a finer mass resolution to some of these smaller knots of gas, zooming in only on them. They saw that over thousands of years, the turbulent environment allows the gas to efficiently lose heat and collapse to form smaller stars around the massive central star. Sometimes there was just one, sometimes there were up to 50. Most of the mass was still concentrated within that central star, but these intricate simulations surprised everyone by suggesting the leftover gas could form far less massive stars. This revelation was of great consequence to those seeking the first stars. According to the mass-lifetime relation, those smaller, sibling stars could live for billions of years. If population 3 stars were formed with only a mere 80% of the mass of our Sun or less, then, according to that relation, they would have been able to live for over 13 billion years. They could still be alive today. And moreover, some of them might even have been swept up into our galaxy, as it formed from the collisions of smaller galaxies. But if these stars do exist, finding them will be no easy task. These small population 3 stars would be extreme rarities among the hundreds of billions of stars in the Milky Way, ancient treasures to be sought amongst the common, modern reproductions. They would also not have led a tranquil life. Over 13 billion years, they would have experienced the pollution of their surroundings by the deaths of their more massive siblings, the formation of the next generation, population 2. The first galaxies too would have formed around them and violently merged with other galaxies, mixing the populations of stars. And so how could we possibly find these first stars? The key, again, lies in spectroscopy. Within the spectrum of these first stars would be signatures that cannot be forged. Their light should be clean of the absorption lines of heavier elements, their rainbow spectrum only revealing hydrogen and helium in their atmospheres. However, spectroscopy is not cheap or quick. Assessing every star would be like launching a full paleontological survey of every square meter of Europe, mainland included, hoping to find the bones of those isolated island-dwelling mammoths. So we must narrow our search to the regions, the islands in the sky, most likely to host what we seek. To provide further complication, their pristine bodies are likely covered in billions of years of pollutants, heavy elements that have accreted onto their surfaces as the universe changed around them, creating false lines in their spectra. And so to determine the difference between population 3 and population 2 requires careful and intensive work. This is archaeology in the truest sense of the word, uncovering evidence of the past by dusting off the layers of dirt. The Milky Way comprises three stellar components: the disk, the bulge, and the halo. The disk is young with star formation, dense with population 1, and no place for an old star to retire. The bulge is the oldest component of the galaxy and is the most obvious to search, except that it is also crowded with young stars, and so shrouded in dust that peering into it is an almost impossible task. And so, that leaves the halo. The halo is the most diffuse of the three components, a low-density area to which stars naturally drift over time. There are fewer stars to sort through here, and there is a natural minimum age, making it more likely to find what we're looking for. Most stellar archaeology has concentrated on the halo, narrowing the search considerably but not solving the issue of camouflage. These old population 3 stars do not dress their age. They cover themselves as their descendants would, giving the impression upon a cursory glance that they contain the heavy elements like younger populations. Their disguise is not perfect though. There are telltale signs of age, such that we don't need to examine the full spectra in fine detail, at least at the start. Iron is a strong line in the spectrum, and not as easily faked by external pollution. Stellar archaeologists initially use iron as a proxy for all heavy elements, and can take crude spectra which first evaluate the strength of this line only. We can scan quickly, looking for stars with the faintest iron lines, and in this smaller sample of candidates, we can afford to look again at a higher wavelength resolution, checking the disguise more carefully. Using computer models, astronomers can estimate the effect of billions of years of camouflage, and work out what abundances we should expect if this is a polluted, pristine star. The ultimate prize is the spectrum that shows no sign of heavy element absorption lines when these allowances are considered and dusted away. As we hone our techniques and sift through the sands, we have become more expert at quickly tossing out the fakes and separating the oldest stars. In 2013, a detailed look at the spectrum of a star labelled SM03136708 revealed no trace of an iron line at all. While we couldn't rule out the presence of iron below the natural light noise of the telescope, this was an exciting discovery. Sadly though, while iron is a robust first indicator of the age of a star, a closer look at the disguise of this star still revealed 4 faint heavy elements, though so few that modelling showed it formed from the detritus of only one supernova. This was a star that had formed directly from the remnants of population 3, a first descendant. By looking at the abundances of those first few heavy elements and the mass of the new star, scientists determined that the population 3 star before it was a star 60 times the mass of our Sun. It likely died in a relatively low-energy supernova, such that few heavy elements from the core escaped before it settled into a black hole. And so while SM0313 is agonizingly close to a pristine first star, it isn't quite there. The search continues. If we find a first star in the Milky Way, it will be a pygmy. There is no other way for it to have survived so long. It would tell us a lot about primordial chemistry and pollution by heavy metals, but it would not tell us as much about the true mammoths that ruled the skies. To learn about these, the long-dead giant first stars, we will have to be more creative. Imagine looking up at the night sky, perusing the constellations you know so well, and finding a star is missing. Perhaps Cassiopeia is no longer a W, or maybe Orion's sword is shorter. Among the 5,000 stars you can see, would you miss just one? In 2015, astronomers were carrying out a survey and encountered this very dilemma. The team were taking new images of the sky and comparing them to previous snapshots. There are naturally variable stars, flashing and pulsing, and there are sometimes bright supernovae marking the end of a star. But N6946BH1 was neither of these. No one had marked this star out as special or worthy of continuous observations, and so it was observed only infrequently. Prior to 2009, observations at that location had shown a red hypergiant, 25 times the mass of the Sun. But in 2009, the star had appeared far brighter, jumping from 100,000 times as luminous as the Sun to 1,000,000 times. This continued for at least 3 months, but the next observation was in 2015, and by then, it was gone. There was no sign of a star, and there was no sign of a supernova, the endpoint that theory predicted for this star. Even when a black hole forms, it does so after the supernova event, the remnant of which lingers in the area for years. N6946BH1 had simply disappeared between observations. Follow-up infrared observations showed a faint glow where N6946BH1 should be, but it was far too faint to belong to a supernova remnant. Instead, it has been suggested that it came from the outer layer of the star, ejected in the final moments before a black hole formed at its core. As the dense core collapsed in on itself, a shockwave rippled outwards, forcing some stellar material out into the wider environment, away from the immediate clutches of the black hole. If this indeed is the correct scenario, as further studies up to current date have supported, then this is the first time we have witnessed a black hole forming. N6946BH1 is the best candidate astronomers have for what is termed a failed supernova, a phenomenon theorized to solve some pressing problems in stellar evolutionary theory. The rate of large star formation is greater than the rate of supernovae, suggesting that these hypergiant stars must be dying in a different way. However, hypergiants are so rare that sample sizes have often been called into question. And this is where the mammoth first stars would come into their own. The era of the first stars, were we to catch a glimpse of it, would provide a playground for those working on theories applicable to modern-day giant stars. And more than that, this rare stellar death is strikingly similar to that which we think the largest of the first stars may have experienced. The exchange of knowledge between those studying ancient and modern stars is two-way. If we have indeed observed a black hole forming without a supernova in the modern universe, it makes it even more likely they formed in the past, too. Sometimes in the early universe, clouds of gas were so large that their lives flashed by in an instant. They collapsed with such force that fusion didn't have a chance to fight back, and the stellar stage is skipped entirely. These direct collapse black holes are thought by some to have seeded the supermassive black holes at the center of spiral galaxies all around us, including our own, a potential solution to the decades-old mystery of how these gigantic black holes got so large. And so having modern-day analogues, whether in the way they live or the way they die, is vital to our understanding of the past. Many mammoths that explorers have uncovered are so well preserved under ice that their hair and even some of their flesh is intact, to the extent that there are stories of explorers feeding mammoth meat to their dogs and even tasting it themselves. The presence of soft tissue has led to the suggestion that scientists could resurrect the species from extinction, but the DNA is ancient and extremely fragmentary. Putting it together into a full sequence is challenging, and can so far only be helped along using the genome of their modern-day counterparts, elephants. And so in space, we can study extremely massive stars, such as Canopus and Betelgeuse, modern-day elephant stars similar enough to share many of their characteristics with the long-dead mammoth first stars. For example, the strength of the radiation and magnetic fields in a gigantic star conspire to cause strong stellar winds, so strong that they can carry off large amounts of mass, steadily evaporating the star. And Population 3 was similarly likely to have strong stellar winds, only accelerating their inevitable and quick demise. But while there is hope of finding a low-mass first star in our neighborhood, or learning from modern-day versions, the search for the truly representative massive first stars can only occur by looking for them directly, and the signal they have left behind. And though this is not an impossible task, it isn't easy. Of course, they are long dead, but they all left a mark on their environment. The fierce stellar winds and strong UV light of the first stars ionized any hydrogen gas surrounding them, knocking electrons loose from hydrogen atoms and forming bubbles of ionized hydrogen in a sea of neutral hydrogen. And this neutral hydrogen, that which isn't affected by the first stars, emits radiation at a very specific wavelength: 21 centimeters. This is because of what is known as a spin-flip transition. This occurs between the proton and electron in the hydrogen atom. All particles have a property called spin. When an electron has the same direction spin characteristic as the proton, it occupies a higher energy level. When that spin changes to be in the opposite direction, however, the electron must fall into a lower energy level. The energy difference is lost as a photon with a wavelength of 21 centimeters. These 21 centimeter photons travel across the universe and land on radio telescopes on Earth. But when a photon from a first star ionizes a hydrogen atom, the electron is released, breaking the interaction with the proton and stopping production of 21 centimeter radiation. This means that if we were to construct an image of what a radio telescope scanning the sky for 21 centimeter radiation could see, it would look like a slice of Swiss cheese, with the holes representing the bubbles of ionized hydrogen and the ionized hydrogen representing the first stars. These bubbles merge quickly, however, and it's not just the first stars that can ionize hydrogen. Black holes can create bubbles too, though not as spherical and neat, and galaxies made of population 2 stars can produce so many photons that before long the entire universe is one large bubble of ionized hydrogen. This transition is called the epoch of reionization, and the shape of these bubbles and the speed at which they appear and merge tells us about what was in the universe. And so, while we may not see the first stars, we can tell by their footprints where they have been and how they grew and lived. Radio telescopes such as the Square Kilometre Array are observing this 21 centimeter radiation and map these bubbles, trying to infer the populations of the first stars and their interactions. But that is not the end of it, for we can also detect the footprints of their deaths. If truly massive stars of about 1,000 times the mass of the Sun do form, then they will collapse so fast that they immediately form a black hole, a direct collapse black hole. If 2 of these entities were to become captured in their mutual gravity, then they would orbit one another, steadily losing energy and inspiraling before an eventual collision. The energy lost in this process is converted into gravitational waves, ripples in space-time caused by the movements of these 2 space-time distorting monsters. In 2016, LIGO and Virgo confirmed the first ever observation of gravitational waves as the result of a black hole merger. The signal from ancient direct collapse black hole mergers will be far weaker due to their distance, requiring more advanced equipment. LISA is a planned NASA and ESA space-based gravitational wave observatory that will continuously monitor the exact distances between 3 space stations. If a gravitational ripple passes through, these distances change, allowing us to detect the waves. The size and frequency of these waves give us a lot more information about the objects that have merged, meaning we would know a little more about the higher end of the mass scale of the first stars, how many there were, and their maximum mass. But direct collapse black holes are the theoretical destiny of only the most massive first stars. Most will end their lives in intense explosions, called pair instability supernovae. These will have been some of the brightest explosions in the universe, and there is a small chance that a telescope like James Webb will capture one that has been lensed in the same way as Arundel. It is, however, another long shot, as these lensing events are vanishingly rare. The brightness of the supernova does make it a possibility, however, whereas the light of the first stars themselves is too far and too faint for us to ever see directly. And so, we have so many methods in play. From scanning the skies for the pygmy population 3s to analysing the 21-centimetre signal of the first massive stars. From capturing gravitational waves of black hole collisions to picking apart modern mammoth counterparts like Betelgeuse, we have a long list of avenues to pursue. Though similar beasts roam the galaxy today, none are quite as unique as those first mammoths. The stars that first lit up the darkness. The stars which, in the cosmological blink of an eye, changed the course of the universe irreversibly, yet died so quickly they never got to see the diversity of structure and life that they sparked. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching. I will see you next time.